That's fine. That's fine. That's fine too. Yeah, so next Kappa. I hope that will be up today. My plan was to get up this morning and I got distracted. It will be due, yeah, tomorrow evening. I'm kidding. I'm thinking next Tuesday. Okay, cool. So I don't know if you guys caught that. Kappa 3, I hope will be up this evening, and it will be due next Tuesday, I think. That's my goal now. Okay, cool. This thing being recorded automatically. Yes. Okay. All right. Yes. Is it really? Okay, it won't be due next Tuesday. It will be due sometime next week, Monday or Wednesday. And I had thought that our first exam was next week, but it's not. It's the week after that. So I'll say more about that in the coming days. Yeah, who cares about fluids? No, actually fluid dynamics is very important in astrophysical context. No, you talk about Mach numbers, you talk about Reynolds numbers. I feel like in space, it's probably not as much, but like the Mars rover, a lot of fluids. That's true. No, even in space, you know, it's not, you know, the viscosity is pretty low, but you can still talk about bulk motions of objects even through the galaxy, so of fluids. Today's the starting picture of the day. Whoa, it's a giant rocket. What's going on here? Moon rising between two starships. So these are launch and return reusable rockets by SpaceX, SN9 and SN10 in Texas, Boca Chica, Texas. I didn't even know that was a launch site. I think that was it? Oh, R.I.P. Oh. Well, it says SN9 was test launched earlier this month and did well, with the exception of one internal rocket that failed to relight during the powered descent. Oh, okay. I see. SN10 continues to go underground and down tests and maybe test launch later this month. That's a pretty cool picture, though. The almost full moon beside two rockets. Okay. Oh, I forgot to share this, so nobody else has seen it. Hopefully Tyler and Dante were able to get on their own APOD site and follow along with us. But now I will share my desktop. Yes. Let's do some. So remind me what we were talking about last time, spectra of stars and how they look really weird and how they don't look the same at all, and how some of them have very strong hydrogen lines, like these A stars over here. And some of them have very weak lines, like, you know, all the other ones. So here's just a sort of a zoom in on that, showing you where we were. I don't have a mouse. I want a mouse, and I don't have a mouse. That's sad. This is actually Keynote. Maybe I need to change the PowerPoint because it'd be nice to be able to point at some stuff. Oh well. Anyway, so stellar spectra, you can sort of see how they change. And this is now the temperature sequence, from the hottest at the top to the bottom, next hottest to the top to the bottom, next hottest to the top to the bottom. You can see they're drastically different. And it's not that they're drastically different in composition, there's something else going on. And that's our goal, is to figure out what's going on and why it's going on for this particular section. Okay, and we did also, I didn't throw this slide up before, but we did talk about this last time, the Bohr model for the hydrogen atom, and which works really well for everything we need. The Lyman series, the Balmer series, the Paschen series. You get absorption by moving an electron up to a higher energy level, and emission when an electron drops back down to a lower energy level. Okay, I now want to talk about how different kinds of spectra are formed. These are Kirchhoff's laws. It's interesting, there are two completely different sets of Kirchhoff laws. One involves circuits, and one involves spectra. I have no idea if those two Kirchhoffs are the same person. They're just both called Kirchhoff's laws. I should look up my physics history at some point, but I've never done that. So, here is the basics, and this is out of an intro astronomy textbook, but that's really all you need. We know that if you look at a hot black body object directly, you see a beautifully smooth continuous spectra. That is the Planck function. And so if you see simply a hot object in space, for example, let's say a light bulb, and light bulbs, at least incandescent ones, although these are getting harder to find, simply have a filament of tungsten or something. You run electricity current through that filament. It gets very hot, and it glows kind of like a black body. And so you get, if you were to look at this thing directly, this is supposed to be an eye. If you can see this over here, this is supposed to be an eye. Looking at this thing directly, you will see a nice, beautiful, continuous spectrum, a Planck distribution. So observing a solid object produces a continuous spectrum. Okay, if you take that same light bulb, maybe the best light bulb I've ever drawn, so don't expect them to be any better than that moving forward. And instead, have a semi-transparent cloud of gas that you're seeing it through. Now, all those photons that are coming through, which are coming out at all colors, are intersecting with this gas cloud. And that gas cloud contains atoms of various types. Perhaps hydrogen. Maybe this is a gas cloud of hydrogen. If it is, there may be some atoms here that are sitting in the n equals 2 energy level. And if they are, and a photon comes along that happens to have a wavelength of 656 nanometers, that atom is going to absorb that photon and bump that electron up to the higher energy level. If a photon comes along with a wavelength 480, it's going to absorb it and bump that thing up to n equals 4. So this gas will be very good at absorbing very particular wavelengths of light corresponding to the energy transitions that happen to be available to it in the gas. And that's just hydrogen. If it's neon or iron or anything else, they're going to have a different set of absorption lines that are produced by this thing. So you still, because it's transparent, you're still seeing most of these photons come through. You still have a nice continuous distribution underneath, but at the points where this gas cloud is able to absorb some of those photons, at that particular energy, it does. And what pattern it is will depend on what gas this cloud is made of, and also where the electrons are in the orbits. So observing a cool diffuse gas with continuous source behind leads to an absorption spectrum. Okay, now, what if you still have a hot light bulb, and there's a cloud of gas here, but you are not observing that cloud of gas with the hot object behind it. Well, this cloud is still getting heated up by this object, by this hot object. It's still absorbing those photons. Those photons are still streaming. You're still it's still doing that absorbing, but those photons are being taken away from a different vantage point, a different angle. And so, well, what happens when a Balmer series line gets created in absorption? What happens to that atom? Well, eventually it's probably going to fall back down. Sometimes n equals 3 and sometimes n equals 2 level, and emit a photon. And that's a process that happens in random directions, right? This thing will also, it's absorbing photons that are going in this direction, but it's emitting them at exactly the same wavelengths isotropically, meaning equally in all directions. And so if you see this cloud without this thing right behind it, then instead of seeing a continuous spectrum, which you don't see at all, you simply see an emission spectrum at exactly the same wavelengths where these guys were absorbed out. So, observing a hot diffuse gas with no continuous source behind it will lead to an emission spectrum. So most, not all, most stars, normal stars, show an absorption spectrum. So what is the, well, we know what the hot object is. That's the interior of the star. What's the cool diffuse gas that it's passing through? Yes, our atmosphere can emit some, but we still see absorption even from space. The star is its atmosphere itself. That's right. It's not a solid object. It has just less and less gas as you go out. And so the photospheres of all these stars, there's still a lot of gas above it for that light to travel through even as it's leaving that star. And so it produces its own absorption spectrum.
What's the middle of the star like that? If it follows this light.
Yeah.
If it follows this solid object other than the fact that there's gas around it.
Right. That's an interesting question. I mean, you could never make that observation.
Right.
But if you could, what would it look like? Well, right. So probably just pretty much black body in every direction you look. Because once you get inside the surface of a star, the mean free path for photons is very short. And so, how far are you going to see? Maybe, inches, centimeters. Will you get absorption in that region? Maybe. I haven't thought about that. That's an interesting question. But you'd never be able to even test out the theory about whether that's true. Okay. So in order to understand spectra, we have to understand atoms. Specifically, how many are in excited energy levels and how many are completely ionized. What do I mean by ionized? What? Electron's been removed altogether. That's right. So if a electron absorbs enough energy, it can leave the atom altogether, and then you have a net positive. An ion, just a charged particle. You have a net positive atom, which is an ion, and a net negative electron, which are both moving around in the soup by themselves now. So some more nomenclature. So for any atom, any element like iron, you can talk about, and astronomers will use this terminology, iron 1 or Fe1 refers to neutral iron. In this case, since iron has atomic number 26 and has 26 protons in its nucleus, that means 26 electrons orbiting about. And the net charge of this atom is 0. Iron 2 is singly ionized iron. +25 electrons, a net charge of +1. Iron 3, you can see how this is a little confusing. Iron 2 is singly ionized iron. Iron 3 is doubly ionized iron, right? The number of electrons that this object is missing, this atom is missing, is this Roman numeral -1. 24 electrons +2. And you can go all the way up to iron 26, 27, 27, iron 27, 26, 26, 27. Anyway, it doesn't really matter. You can only lose 26 electrons before you're at all of them, but I think that would get you to iron 27. Yeah, that makes sense. So that's the terminology. So these are ions. These iron atoms have been ionized, singly ionized, doubly ionized, and you can have as many of these, of course, as you want. Let's talk about some statistical mechanics for a minute. Some of you are taking stat thermal right now. There's a whole section on stat thermal in your book that we skipped. We're not going to get all that deeply into it. We just need a couple of important results from StatMech that we can use to our advantage in stellar astrophysics. So here are some highlights from statistical mechanics and thermodynamics. A lot of this stuff we cover even in Analyte 3. So what does it mean for a gas to increase the temperature? What is physically happening to those atoms? If you increase the temperature of a gas, what happens to the atoms? Yeah, sure. And therefore they're moving faster. They're moving kinetic energy. Temperature is basically a measure of the kinetic energy of the gas. If you increase the temperature of that gas, the atoms and molecules and whatever makes it up have to be moving faster, either vibrating in their lattices or moving in some gas fluid situation. And still usually a vibrational thing though. In order to have temperatures, you have to have collisions. If you have no collisions, you can't even really define what the temperature is. So in some level, it's the velocity distribution that defines that temperature. So do all atoms move at the same speed at a given temperature? No, there's a whole distribution of speeds that go along with the characteristic temperature. And those speeds, of course, depend on things like the temperature and also the mass. And that is the Maxwell-Boltzmann distribution. We wrote this equation down in Analyte 3. And it looks like this, NV dV, the number of particles, the number density of particles moving at a velocity v, modulo some change in over some infinitesimally small area, velocity range dv, is equal to the number density of those particles, m over 2 pi kt to the 3/2 e to the mv squared over 2 kt times, and this is now outside the exponential, 4 pi v squared dv, where n is the number density of particles, m is the mass of particle in your gas, k is a Boltzmann constant, T, of course, is the temperature. And NV, this thing that we're actually calculating, is the number per unit volume with speeds between V and V plus dV. Sorry? Didn't hear it, didn't get it. It's kind of gross. Yeah, these are all kind of gross equations. It's true. But if you plot this up, and we did it in Analyte 3, you probably can do it in Stat Thermo. I used to do it here, but honestly, it looks exactly the same as the Planck function. You have some velocity squared, which is going to make things get big until this e to the 1 over, wait, there's got to be a negative sign there, doesn't there, somewhere? This has got to be a negative. Until this inverse exponential takes over and just kills it on the other end. It looks almost exactly like the Planck curve, right? So at a given temperature, you're going to have a nice characteristic range of velocities. It's not, there's non-zero chance of having any velocity, but of course, most of it is in a velocity range that is important. So you can, I should have written this down. What does it look like? Let's just NV as a function of V, right, will look something like this. So how many particles are moving? This is like a histogram then, right? The number density of particles as a function of speed, you'll get a this distribution looks something like this. And I didn't write these down, but you know, the characteristic, like 3/2 kT, you're gonna get the peak. And you know, 2 kT, there's the median and the mode, you know, things that are about kT-ish. That's not even right because there's an M in there, but you get the idea. I didn't write it down. I don't remember it off the top of my head, but it doesn't really matter. Those are equations we wrote, you can look up easily. And we wrote down in Analyte 3 even. So if you can go back and look at your notes there, and it's in Bob too. Do I have, there they are. The Maxwell-Boltzmann distribution for, these are degrees Celsius, not Kelvin. I'm not sure why they did that, but you get the idea. So the cooler you are, the smaller the range, the smaller the average velocity of the particles in your soup are. Increasing the temperature, of course, this has to come down because this integral has to, well, this is also for some, this is not, this would be normalized so that it's a velocity distribution function and it should integrate to 1, but they've actually times it by a certain number of particles here. But it doesn't really matter what the scale is. You know, you have taking the same number of particles and you're spreading them out actually over larger velocity range. And so this peak gets smaller, but that just means we're moving them out to larger velocities. So an example of the Maxwell-Boltzmann distribution. It's not the Planck function, but it looks a lot like the Planck function. So this is for room temperature gas of different noble gases. I don't know what that is. But these are, all right, so I covered it over. These are now different kinds of particles. They're different masses of particles at the same temperature. Which one of those is the most massive? Liam. The purple one. That's right. The more massive you are, the slower you're going at the same temperature. Why? Because it's really an equal partition of energy. And so the kinetic energies at the same temperature, the kinetic energies of all of these objects on average are the same. And that means the low mass ones have to be moving faster and the high mass ones have to be moving slower. Oh, xenon, argon, helium, neon, and helium. There you go. Bingo. And you can see here's hydrogen atoms at 10,000 Kelvin, right? This is at the surface of Vega, and how fast they're moving. And you can talk about the most probable, and the RMS is a little bit larger than that, meaning the root mean squared. And again, if you want to know how many atoms are at a particular speed, you have to integrate between two speeds to get that actual number. So, excuse me. Again, this is a distribution function, which means that the odds of getting exactly this velocity is always zero. You always have to integrate over some range to get any non-zero number. Okay. So, as atoms collide, so what's happening in a gas, right? If you follow a random molecule or atom, it's just bouncing around, running into other stuff in the gas. As those molecules collide and those atoms collide, they can impart energy into each other. And that energy can go into simply collisional kinetic energy, but it can also go into exciting those electrons into higher energies. And so we expect the hotter a temperature of a gas, the more atoms will be excited to higher electron energy levels. And this is very important for understanding stellar spectra. So you've got a gas of hydrogen atoms. It's in a box. It is, you can define thermodynamic equilibrium when the things have sort of settled down. That's not to say these things aren't still running around and bumping into each other, but on average, this distribution holds and doesn't vary far from it for all the particles in the gas. And other things in the gas become steady. Large scale properties of the gas, the pressure. You can define a pressure at all sides of that gas. So thermodynamic equilibrium defines a state where things are not changing rapidly. As long as you wait long enough and aren't importing or taking out energy, you will eventually reach a state where things are steady. And it is really only then you can even define the temperature, because if things are changing, you can't really even define the temperature. But once you can, then let me just write this down. The gas of any atoms will eventually reach a state where the fraction of atoms in each state remains constant. And we call this thermodynamic equilibrium. And this is important because it allows us to do some things statistically that we couldn't do if this weren't the case. And in fact, when you go to astronomical conferences nowadays and you're a stellar spectroscopist and you're worried about these things, a hot topic is non-LTE effects. LTE being local thermodynamic equilibrium. What happens when this isn't strictly adhered to, and what modifications do you have to make to your theories to account for that? We're not going to worry about that. We're going to just think about what the local thermodynamic equilibrium states are. So basically, this implies that all the behaviors of the bulk system are constant in time. So we need an equation that relates the expected values. And by the expected values, we need to know, if we're going to understand these spectra, we need to know how many are in the ground state. We need to know how many are in the first excited state. We need to know how many of those electrons are in the second excited state. Because we can't interpret those spectra if we don't know where the electrons are in those atoms. We need an equation that relates these values. It's not discretized though. It's called the Boltzmann equation. He didn't even have to share this one with Maxwell. He's just on his own on this one. And the Boltzmann equation gives you this ratio. So NB over NA. We write down all these equations, all these symbols, and then we'll define them in a second. GB e to the negative capital EB over KT divided by GA e to the negative EA over KT So that is in fact the entire equation. We can combine these two exponentials if you prefer to have a single exponential. This is equivalent to GB over GA times e to the negative EB minus EA over KT. So let's define these terms. NB and A are the number of atoms, sorry, not atoms, number of electrons. Oh, that's right, the number of atoms with electrons in levels A and B. So this is going to give us a ratio of number of atoms with electrons in energy level B to number of atoms with electrons in energy level A. We know what these G's are. Probably talk about these at thermodynamics, but we might not have gotten to them yet. These are statistical weights. Of energy levels A and B. This describes how many quantum states exist at each of those levels. In hydrogen, for example, in the ground state, has G equals 2. There are 2 quantum states associated, this should be a has, with the ground state of hydrogen, with the electron in the ground state of hydrogen, and that is spin up and spin down. The electron can either be spinning in the same direction as the nucleus, as a proton at the center, or it can be spinning in the opposite direction. Those are 2 distinct quantum states, and that gives the ground state of hydrogen a statistical weight, a G. The G1 for hydrogen would be 2. The general form for hydrogen is Gn equals 2n squared. Because you get different S and P and I don't know. I don't even understand it all. It doesn't really matter. This is all you really need to know. The chemists have figured out all of these statistical weights for us. And the atomic physicists. Let's give the atomic physicists a shout out. It's also true that we know what these E's are for hydrogen, the actual energy levels of each of those hydrogens. And that is negative 13.6 EV over n squared. We know everything. For hydrogen, this is a solved problem. You can always, the only thing that's left in here, we've got the G's, we've got the E's. is temperature. This is going to change with temperature, but everything else is known for hydrogen. This is a simply solved problem. So for EB greater than EA, we almost always do it this way so that the higher energy level one is on top and the lower level energy one is on the bottom. At very low temperature, what happens? This is going to get very small. This is going to get very large and negative, and almost no electrons show up in the B anymore. Let's think about this one. This is going to be a constant. As this gets large, this gets small, this whole thing gets large and very negative, and this thing goes to 0. So at low temperatures, we expect almost all of them to be in the lower state compared to the higher state, and that makes sense. At very high temperatures, this goes to 0, and this goes to some number, and this becomes a non-zero number. This never gets exponentially large, but it gets roughly even. And even a little bit more than 1, because these B's are usually, these statistical weights usually go up as you go up. So if this becomes really, really small, this becomes 1, and then your ratio just becomes down to the statistical weight between those two energy levels, which is a number that's not exponentially rising, but is usually well over 1. So the very high temperatures, you expect most of them to be in high, which is what you expect. This equation is doing that for us. Low temperatures, they'll be in the ground state. High temperatures, they'll be in excited state. Let's pull out Mathematica. I forgot to warn you that that was happening today. If you want to follow along, if not, you can just, I'm recording this, I'll post the Mathematica sheet. It's up to you. Go away. Thank you. Yeah, of course. Right. So that's going to give you whatever, 4 to 1, 3 to 1, 2 to 1. You're going to have to do this a bunch of, if you want to know where all of those electrons are, you're going to have to do this probably not an infinite number of times, obviously, because it's going to, be clear where things are at, but you're going to have to do this a lot. That's right. It's going to take some modeling, probably. I mean, people did this by pencil and paper, but that was hard. And who wants to do that? That's right. You're going to have to build up some statistical models. So I'm going to do, why am I going to do this? Do I want to, right. I'm going to need Boltzmann constant in EV, because this is going to help me I have this in EV. If I have Boltzmann's constant in EV, then I don't have to worry about anything else. So KEV is going to be quantity magnitude, which is, again, just the number associated with the unit convert, quantity, Boltzmann's constant, and I want to convert that to electron volts per Kelvin. This is a useful way for, let me make this a little bit bigger so you can see it better. Can you see that well? So this is just going to give me the number of the Boltzmann constant in units of electron volts per Kelvin. And it's going to just give me the number. I know, it's very useful. Great. I don't know why it gave it to me as a fraction, but it doesn't really matter. It's a small number. All right, so let's define GH, which is going to be the statistical weight for hydrogen, as a function of n, to be 2n squared. And let's define the energy of hydrogen as a function of n to be 13.6 divided by n squared. And this will be an EV, and we can combine these together and everything will be, our energies will all be in EVs, and they'll cancel out, and the temperatures will be in kelvins, and they'll all cancel out, and this should just work. I can make this, okay, cool. Now I can define my Boltzmann for hydrogen, and I need two, I'll call it N2 and N1. And it also needs to be a function of temperature. We have three things now. And this is going to be GH of N2 divided by GH of N1 times exp of negative EH of N2 minus on the top EH of N1 divided by, oops, KEV, which is the number we'd already calculated up here, times T. And that should just work. Now we can plot this thing. Plot BH. Let's just go from 2 to 1. Let's see what the ground state and the first excited state for hydrogen as a function of X, temperature we're going to change, and let's go temperature from 0 to 20,000 Kelvin. How about that? So what is this going to tell us? What is this going to show us? This is going to show us the fraction of electrons that we expect to be at the n equals 2 divided by the n equals 1 state for hydrogen as a function of temperature from 0 to 20,000 Kelvin. It's pretty exciting. You want to know what this thing looks like? You've never seen this before. It's like a whole new thing. Ooh, that's not what I was expecting. What did I do wrong? Is that what yours looks like? Yeah, it should be the other way. What did I do wrong? Negative 13.6, thank you. That'll do it. You get the star for the day, Morgan. That's what it should look like. Oh, then you might have forgotten this negative sign. You have that one too? You need one there and there. And this should be what it looks like. So what is this telling us? The sun is about 6,000 Kelvin. Remember, Vega is a 10,000 Kelvin star. As you go, you're talking about really hot stars here out at 15,000 Kelvin. Are there a lot of atoms in the n equals 2 energy level for hydrogen? No, we're at 0.06. Less than 1%, even at 20,000 Kelvin, less than 1% of all atoms whose electrons are at the n equals 2 or n equals 1 level are at the n equals 2 level. They're still all at the ground state. Almost, but not all of them, but a lot of them. At what temperature do you think it is that N1 equals N2? We could go out of ways. So let's see if we get it at 40,000. Whoa, what happened? Go away. We're still not to 50% though. How hot do you have to go? And we could go and we could do this, but we can use Mathematica to solve this for us numerically. Let's try solve BH of 2 comma 1 comma X equals 1. Actually, to get to 50%, we need that ratio to be 1, right? For half and half. We want that ratio to be 1. And let's solve that for X. At what temperature are these two things equal? And we get 85,000 Kelvin. Holy moly. That's a lot. It's a huge amount. Let's go back to our A stars. Let's go back to all of them. Okay, so we can now see why it is that stars' Balmer lines get weaker and weaker and weaker as you go towards cooler and cooler stars. Why is that? Right. In order to have a Balmer line, you have to have an atom starting in the n equals 2 level. And even at 10,000 Kelvin, almost none of them are. But as you go cooler, even far fewer and fewer of them are. And so, yes, the sun is entirely, and these stars are entirely hydrogen, and you get some pretty strong Balmer lines here, but they go away completely, not because these stars don't have any hydrogen, but because 0 of that hydrogen is in the n equals 2 level to form that line. They just aren't, the atoms are there, but they're not in the right electronic state to be able to form that line. Did you have a question, Rizma? Okay. Okay, so now we can understand why the Balmer lines get weaker as we go towards cooler temperatures. But why do they get weaker as we go towards hotter temperatures? These O stars still aren't 80,000 Kelvin. Why is it that these lines get weaker again as you go from 10,000 to 20,000 to 30,000? Yes and no. It's not that they're still bound, because you can imagine if this ratio is bad for 1 to 2, it's even worse for 1 to 3, it's even worse for 1 to 4, it's even worse for 1 to 5. So even for a 20,000 Kelvin star, 90% of the atoms are in the n equal, more than 90% of the atoms are still in the n equal, in the ground state.
Because if they go up, they're like, you have more going up, but that means you have more photons being emitted as well. So then they have the possibility to run into other ones and not affect that.
No, that's a good guess though. They're getting ionized. And I don't know why this is, but somehow, for some reason, it's easier to be ionized than it is to be stable at a larger, and maybe it's, honestly, I don't know the physics of this, but it's kind of interesting. This is a short-lived state, right? An electron gets excited because it bumps into something. It's going to pretty quickly cascade back down. It's not going to be there for very long. An electron gets ionized. That's going to be a longer process. It's going to have to come across another free electron. They might get separated. That could be a longer term thing. So it might be that even though ionization is fairly rare, unionization, capturing the electron back, probably takes a lot longer than it takes to cascade back down for these higher energy levels. So we need another equation. And that equation is going to be how many, for a given temperature, how many atoms are ionized as opposed to unionized for a particular atom. And that is an equation which I don't have time to write down, but we'll write it down next time, and it's called the Saha equation. And that will give us our final piece for being able to interpret these silly stellar spectra, at least for their hydrogen lines. See you on Wednesday. Sure.